And we express the entropy in terms of its partition function. And then we inserted the terms we had obtained previously for the heat to arrive at then the usual expression for entropy as integral over heat capacity scaled by inverse temperature over the temperature range. We then wanted to discuss an example, and in particular, we wanted to revisit the entropy of the ideal gas in analogy to the internal energy of the ideal gas, which we had already discussed. And I believe this is my subchapter F. So we want to make use again of our partition function, and we inserted this in our expression for the entropy, the generic one, which is the same as what you see on the right-hand side. And we have the capital Q. We could then simplify the expression with Stirling's formula, and that's where we left off last week. Okay, so we continue now, and we have now 5/2 kBn. I'm taking the kBn from here and slap it on top of my 3/2 plus my kBn logarithm Q divided by n, which comes from uniting these two terms. Okay. Now, as a next step, I'd like to move to the molar entropy. So dividing everything by Avogadro's number, we then obtain for the molar entropy 5/2 R, the ideal gas constant, plus R logarithm Q over N. Okay. So by now, we have simplified to the degree possible the expression in terms of reducing the partition function from the capital Q to the Q for a single atom, for the single atom system, the small q. And we are now ready to insert our expression for that. So if you wish, this is the moment where we insert the ideal gas partition function. Now nothing happens with my 5/2 R. And let's now just insert the term. It's our 2 pi m over h squared beta raised to the 3/2 and the volume. And now I still have my n from the expression above, right? So that's a very neat compact expression. I can now unite the constants, the 2 pi and h squared with the 5/2 r, and you will obtain approximately 18.6 r. And now I take out my molar volume. I split it out from my logarithm, and then I keep explicit my mass, right? So the mass is something we still want to be able to vary, and the temperature as one more term. Now my volume I can also replace by RT over P, and then I obtain 172.3 joule per Kelvin and mole plus R logarithm. And now I unite my variables. That would be my m to the 3/2, and my temperature is now the temperature from before the 3/2 plus the temperature from my substitution here. That gives me 5/2 for T. I'm still left with a gas constant also from the substitution, the RT over P, and divided still by the pressure. Okay. So what we have here is a system and condition independent term. Okay. And then we see that the entropy grows with the logarithm. So if the entropy grows if your logarithm 3/2 logarithm of m grows. It also grows with 2.5 logarithm of your temperature. And it shrinks with the logarithm of the pressure. Right? So if your pressure goes down, your entropy goes up for the ideal gas law. Right? So this is a pretty neat result again, right? But it's approximate and based on the partition function of the ideal gas law. But nevertheless, you can immediately extract some intuitive notion here. Yes, please.
We assume that that pressure decrease causing entropy increase is under constant volume, or are we allowing the volume to change when we do that?
Yeah, so everything by default we fix everything else, right? And so it's like these discussions of how things depend on each other is an excellent question, and it's something deeply scientific. How does some property, some function depend on ... Okay. And the answer, the mathematical answer to this is, it's not put ... but x, y, z. The mathematical answer to that, and no, I should say the physics answer to that is it's the derivative. The derivative is the slope in that variable, and that will tell you about the dependency, right? So if f is independent of x, the slope will be 0, right? So I'm saying it's physically. So let's write down that answer. df dx. And that is typically keeping y and z fixed, okay? Now, of course, if you start changing in that direction, they might not be independent, and then you have to consider cross-coupling terms. But these would then be higher order terms. That's why I corrected myself. Mathematically speaking, you should consider all derivatives, right, for the dependency. But in physics, we like to assign more importance to lower order terms. Any further questions on this? This dependency business is really a very important thing generally throughout physical chemistry. You can ask this question, right? How does one thing depend on the other? And then you should always look at the derivative. Sometimes even in experimental sciences, you might be interested in such a question, right? But you might not have a model for evaluating a derivative. But what you can then do is do a finite difference, right? You could change, if you have a knob in your experiment where you can change something, like the acidity, for instance, the pH, and then you want to measure the change in yield or reaction rate, right? You can measure that. And then you have an experimental derivative, right? That tells you something without having even to establish a model, right? So it's a very powerful question your colleague asked here. All right. Sorry, this was a little bit of an excursion, but I think it's sufficiently important to justify that. I should still stress that this boxed equation here carries a name because it's so cool. It's the Sackur-Tetrode equation. And if you deal with a gas, right, assuming that it's sufficiently ideal, it's always worthwhile to consider this. Are there further questions? Yes, please.
Function represented by small q or the capital?
So thank you for letting me clarify this. The capital Q was for the entire ensemble, for your entire system, right? All the particles in it. And because we said in the ideal gas, the particles are indistinguishable and they are weakly interacting, because of that, we could write it as a product of many small q's for each atom. So for each atom, you have a small q, right? So if you wish, it's the molecular q, the microscopic q, really, of your individual atom or your individual molecule. while the capital Q is basically the macroscopic partition function of your entire ensemble, which you would never dare to evaluate, right? Does it make sense? No problem. All right. I'd like to finally, so if this was F, then G is going to be our next subchapter. I'd like to finally come to the case where we try to use everything we've discussed so far in order to demonstrate the second law of thermodynamics. Right? So let's finally consider the second law. Okay. Now, we are doing this by looking at isochoric heating. What does that mean? It means we have a temperature change without changing the volume, right? And as soon as the volume changes, you should always think work, right? Now we don't have any volume change, so this means no work, okay? There is no work. That's what these two symbols mean. Or no volume work. So, right, we know that dW minus PdV would be 0, right? So this means if I take two containers and they don't need to be the same volume, but one is container A, the other is container B, and there's some isolation wall between them, right? So I have a TA and a TB. Let's maybe save space and write it right away like this, okay? And now the process I'm considering, the change in entropy, is when changing this system into a system where now the two systems were put in touch with each other and we have one, so A, B. We have one temperature, right? So TA and TB have come to T, right? And that must be happening because of the zeroth law of thermodynamics. Okay. Okay, so if we now consider this case, right, we could look at the change in the energy of part A, right? And now this is dq, and your dw is 0 because we kept it isochoric. And then I can divide this by the temperature of TA. And if I do this, you see that I just obtained my entropy change of the container A, right? Similarly, we have for dUB divided by TB dQ over TB equals DSB. Now, I have these two containers. In the introduction of the entropy, we already have made use of the fact that it should be extensive. So I can, for the entire process, write ds tot, ds total equals dsa plus dsb. And now I have these nice two relations here, that this must be equals dua over ta minus dub over tb. So far, so good. Now we use the first law. Things must be conserved. So the change in one container must be equal the change in the other with opposite sign. This means dua equals minus dub. As a question, yes, please.
Why is it minus du?
Oh, I'm sorry. Of course. Thank you. Good catch. But this minus here is for real. I think I was getting ahead of myself, right? So as my energy in one place goes up, in the other place it has to go down by the same amount. Now insert this, and we see that our ds tot must be equals dua 1 over ta minus 1 over tb after we have factored out the dua. Okay. And this basically already proves to us that your change in entropy has to be positive. Consider the following. If your TB is larger TA, right, then the DUA, so A will have a lower temperature, right? And so A will gain the heat, it's missing heat. So this one will be larger 0, right? If the TB is larger TA, then 1 over TA minus 1 over TB will also be larger 0. Okay. And that then means I multiply a positive number with a positive number, and my ds tot is larger 0. Now, else if TA larger TB, well, then my DUA must be smaller 0. But also my 1 over TA minus 1 over TB must be smaller 0. And so if I multiply two negative numbers with each other, I get again ds tot larger 0. And as if TA equals TB, which is the boring trivial case where nothing has happened, right? Well, then UA, the change in A must be 0. And the difference between the inverse temperatures must also be 0. And so in this case, ds tot equals 0. In other words, no matter what you do, ds tot will always be equals or larger 0, which is the second law. Now, this topic of the second law is often falsely misrepresented in the general culture, right? This is true for the system, right? But you could construct an environment which actually reduces the entropy in the system. And you encounter this a lot in the chemical studies when systems have been pre-organized. And so there can be processes where entropy is actually not gained, but you will have to pay for that in terms of the entropy of the environment. And so again, if you count the environment together with the system, then that total entropy change will be larger equals 0. Are there any questions on this? It's all clear. All right. I would then like to move to our chapter number 4, where we will be talking about the different degrees of freedom or the different modes of energy. So let's call it degrees of freedom. And in particular, I'd like to discuss with you now that we can separate by energy modes. Okay, so you have probably realized already I can use various functions in physical chemistry to refer to different physics, right? If I talk about the energy, you can ask, is this the potential energy? Is this the kinetic energy, the free energy, a correlation energy? So you always have to think which energy, okay? And I can also make that distinction, or basically partition my energy onto different regimes and different physics which constitute your system. And I'd like to show you a little graphic where I'm now sharing a different figure. And this is this figure here, where you see on the y-axis the energy of the H2 molecule. And on the x-axis, you see the nucleus-nucleus distance. This energy is measured in electron volt and the distance in angstrom. Now, H2 is one of the simplest molecules. We have 2 electrons with 2 nuclei, each consisting of a proton. Maybe you have already seen the electronic term symbols used for the wave functions, right? The symmetry of the wave function is denoted by these Greek symbols, and the changes in sign by the U and the little g standing for gerade and ungerade. So pair and even and odd. You might be familiar with this idea of these electronic levels looking at molecular orbitals. Right? I'm not sure if in your last quantum course you've seen this, but that is basically what this is referring to. Now, these molecular orbitals, they would deform slightly as you stretch the interatomic distance, and your energy eigenvalue then varies as shown as these solid lines. As you stretch the bond more and more, eventually you reach the case where you have the isolated atoms. In the lower curve, it would be the 2 hydrogen atom in the electronic ground state. In the upper curve, one of the hydrogens is in the 1s state. The other hydrogen is in the 2p state, to which it dissociates in the first excited electronic state. Now, I like this figure very much, and it is sort of iconic for the field because it also indicates the vibrational levels. So you see now for the electronic ground state solution, you see entered as horizontal lines the solutions to the vibrational Schrödinger equations. Okay, so each one of these levels is a vibrational level, right? And you also have an entire set of solutions for the first excited electronic state. And I can play this game once more for the rotational degrees of freedom. So on every vibrational level in your ground state, you see a whole bunch of small horizontal lines. These correspond to the different rotational solutions to the rotational Schrödinger equation. Okay? And we have that for every vibrational solution. And for every vibrational solution, and for every electronic solution, we have all vibrational and all rotational solutions. Okay? Now, what is nice here also, and please note, these solutions, they live on different energy scales. You see the spacing between these levels, right? The spacing between the electronic levels is much larger. This is where we have UV, vis, X-ray, right? You need much more energy to go from one electronic state to the other. The vibrational levels are already much closer together. This is infrared, right? This kind of spacing, right? much less energy is carried at such frequencies. And then the rotational modes are so close by, we can hardly distinguish them on the scale, right? Now, I'm showing you this because I want to convince you, and I need to change back again to the lecture notes, because in the chapter we are talking about now, we will be making heavy usage of these different modes. In particular, what this means is that we can approximately, so the energy is approximately additive in various modes. Okay, I'm writing approximately here because you should remain aware of the fact that there can be coupling between the modes. In particular, imagine you're stretching your bond, right? What will happen to the electronic levels, right? What will happen to the vibrational levels? What will happen to the rotation in those, right? As the shape of your potential becomes flatter and flatter, you can have coupling between the modes. And indeed, there's something known as rho vibrational spectroscopy that exactly tries to elucidate such coupling. But for this introductory lecture and for most intents and purposes, this approximation is just fine, right? And so what this means is that our eigenvalue of some level, right, can approximately be written as the eigenvalues of a translational Schrödinger equation, of a rotational, of an electronic, of a vibrational, of a spin, and maybe external fields and whatnot. Okay, so all the things that all the physics you can imagine, relativity, whatever, right? All that stuff. And we write that approximately as simply a sum. Okay. Now, it gets really interesting when we consider what that means for the partition function. Let's consider impact on. Okay. So suppose you just have two modes, and let's call them alpha and omega. Okay. And suppose they live in some state K and R. Okay. States, meaning those are the different solutions in your Schrödinger equations. One for omega and one for alpha. Right? Each mode gets its own Schrödinger equation. Then your Q of the total thing could be written like this, where I have a beta epsilon 0 of the alpha mode times e to the minus beta epsilon 0 of the omega mode. Right? And now I need to go to the next state. And I continue the sum until I reach e to the minus beta. Now I did all states for my omega node. Ns omega. Okay. Now I always had this e to the minus beta epsilon 0 in front of each term. But now I have to repeat the exercise, but with the next state for the alpha mode. Okay. And I have to do this until I reach, at the end of the day, an expression where I have done this for all NS alpha states and all NS omega states. Assuming that in the alpha and the omega state, you have the same number of states. We just assume it's some large number, okay? Okay, so that's basically my Q, my partition function without using the summation symbol. Now I can do a neat trick. I can factor out the constant terms, right? I have a minus beta epsilon 0 alpha, and then I multiply this with the sum over all omega nodes, right? Plus e to the minus beta epsilon 1 alpha, again, sum, right? So ns alpha times my bracket. Now this bracket, of course, is nothing else than a partition function for my omega mode, right? Now I can factor out that partition function, right? So let me write that in front, and then I have e to the minus beta epsilon 0 alpha plus e to the minus beta epsilon 1 alpha, and so on until e to the minus beta epsilon ns alpha. But again, this is just the partition function this time for alpha. What this means is I can write my Q tot as a product of partition functions of the various modes, energy modes in my system. If and only if they are additive, right? This is known as the separation of the partition function, and it is crucial for an in-depth discussion, which we will have in chapter 4. Are there any questions? No questions. We are already after the hour. I'm sorry I went 2 minutes too long. I'd like to thank you for your attention, and I'll see you on Thursday.